This is section 6.1. Professor Aguilar talked about all the theory behind the inductor. So what I'm going to do now is to present some example problems. But before we go into the example problems, I want to quickly summarize because we covered a lot of ground in section 6.1. Okay, so Aguilar gave a bunch of formulas. The first one is the relationship between voltage and current in an inductor. Okay, the voltage in an inductor is L times the derivative of the current, the time derivative of the current. So this is one formula that we are going to be using in the example problems. Now, if you are to write the same relationship between the voltage and current as a function of voltage, okay, current expressed as a function of voltage is 1 over L, the integral 0, t0, okay, t0 to t v of t dt. Okay, so this is the second equation that we are going to be using in the example problems. Now, the third is about the energy stored in an inductor. Okay, inductor and capacitance can store energy and we can get a measure. Okay, so this is the if the initial energy stored in an inductor is 0, okay, then the energy stored in an inductor with an inductance L and current I flowing through is L 1/2 Li squared. Okay, so when we are looking at energy calculations, energy stored, we use this formula. Now, let me give you a side note. This is something we are very familiar with. 1/2 mv squared is the kinetic energy of a body with mass m and velocity v. Okay, 1/2 kx squared is the energy, potential energy stored in a spring with a spring constant k and elongated to a distance x. Similarly, you will see that the energy stored in a capacitor, we are going to look at that, is 1/2 CV squared. The idea is that this format, this canonical form of 1/2 times a constant times a variable squared for energy stored is something fundamental we have seen multiple times in the past. Okay, so that's number 3. Number 4, so we are looking at a quick summary of section 6.1, a fundamental property of inductor, that is number 4. The current in an inductor now cannot change instantaneously. Okay, it cannot change instantaneously. If it does, it leads to infinite voltages and potential. So physically not possible. Now, the fifth and equally important relationship is about the power. We know the power is always the voltage times current. So the power in an inductor is the current multiplied by the voltage, which I know from equation 1 that it can be written as L di by dt. Okay, so L I times di by dt. Okay, so the power stored in an inductor is Li di by dt, the power consumed, absorbed, or delivered. Okay, the power of an inductor is L di by dt. So this is a quick summary. In the next video, we will start looking at some example problems.